Hi there, and welcome to video number 13 in the calculus of variations. In the last video I said I would prove something called the fundamental lemma of the calculus of variations. Now we left it last time saying if you had the integral of the form integral from x1 to x2 of partial f by partial y minus d by dx of partial f upon partial y derivative all times some other function beta of x by dx, in order to make that whole thing equal to 0. Now we're assuming e to x does not equal 0. If that doesn't equal 0, we're trying to prove that this section here must equal 0 in order to make the whole thing equal to 0. Now it might appear that that's obvious because we could write that as integral from x1 to x2, and if we replace this whole thing with just a function, we'll call it u of x times beta of x by dx equals 0. Then you might say, well, if that doesn't equal 0, in order to make that whole integral equal 0, then u of x must equal 0. It's like saying, let's say e to x is a number 5. So 5 times what equals 0? Well, 5 times 0 equals 0. If it's 100 times what equals 0? 100 times 0. So you'd have to always multiply it by 0 in order to get this integral equal to 0. Now that seems maybe a bit too obvious, but who's to say that there isn't some strange concoction of differentials here in this section here which makes that equal to 0 without this section being 0. Now the fundamental lemma of calculus of variations proves that that isn't the case, that that must always be equal to 0, and that's the proof which we're going ahead to have a look at the moment. Now let's draw in a curve. Okay, that curve is curve of y equals some function s of x. Now let's look at that here, point 30, let's at that point there, P1, that point there by B point A, that be point B. Then we're going to prove by contradiction that this here must equal 0 in order for that to equal 0. So by contradiction we're saying that this must be 0. So let's make the contradictory remark that that doesn't equal 0. So I mean u of x does not equal 0. So let's say u of x does not equal 0, and see if we can find the contradiction that occurs whenever we make that statement. Now for any points along that curve s of x, then in order for u of x not to equal 0, okay, so there's u of x there. Remember, u of x is the variation on this curve. Okay, so that's a variation on the curve. Okay, now we're saying that u of x doesn't equal 0, so there's two options. U of x can be greater than 0 or u of x can be less than 0. So let's assume u of x is greater than 0 for all points along that curve. That means that u of x must be sitting above this line, because if it went below the line it would have to cross over, and at that point u of x would equal 0. So u of x always sits above that line there, so u of x is greater than 0, it's always positive. Now if we look at the other function, eta of x, if we choose the function eta of x, okay, so let's choose a function eta of x. Now the one I usually choose, for example, to show this, eta of x equals x minus x0 times x1 minus x, and that would be for all x greater than equal to p0 and less than or equal to p1, and everything outside those values we'll just put in else equals 0. So if we were to put in that coordinate axis there, which is our x, and that coordinate axis there, which is our y, then this function here, well, that part of it, that's y equals x. Y equals x looks like this, but it's y equals x minus x naught, so there's x naught there, so it's y equals x, but it goes through x naught, so there's a line that runs through here like that. Okay, and this here is y equals x1 minus, that's just x, it's not x2, it's just y, x1 minus x. So that's y equals minus x runs like that. So minus x plus x1 is a line that runs through here like that. Okay. Now this here, and anything outside is defined as 0. That's what this part here says. Anything outside, that's only defined for a section P0 to P1. Everything outside is 0. Okay. So this function here is a positive times a positive is always a positive. It's always positive between these 2 points. Okay. So that means that eta of x is greater than 0 between these 2 points. So that means if we find the integral of u of x, eta of x by dx from some value, say from a to b, that would equal, well, if we integrate it from here to here, eta of x is defined as 0, so the value at that point would be 0, and when you integrate it from p1 to b, again the value would be 0. It only exists from p0 to p1, so that would be the integral from p0 to p1 of u of x times eta of x by dx. That's greater than 0, that's greater than 0, the whole thing then is greater than 0. Now by the same argument, if we chose a value u of x not equaling 0 and we make u of x less than 0, that's a negative value, then working through we would have p0, p1, and it would be u of x times eta of x, oh right, it's getting worse now, by dx would be less than 0. Now we have these two identities here, and here's where our contradiction occurs, because we know that if eta of x is greater than 0, then this whole integral must be greater than 0. If eta of x remains less than 0, the whole integral must be less than 0. So that means that when eta of x actually equals 0, the only option is for the integral here to equal 0. So when u of x equals 0, the only option is for this to equal 0. What's going on? What's that? No, that's it. Right, okay, so that means that if u of x equals 0, then this integral can't be greater than 0, because it can only be greater than 0 if u of x is greater than 0. It can't be less than 0, because it's only less than 0 if u of x is less than 0. So when u of x equals 0, that integral x0, x1, u of x, eta of x must equal 0. It's if and only if u of x equals 0. So that's the little proof called the fundamental lemma of calculus of variations. Okay, thank you and goodbye.